start streaming. Yep. You're getting them back in a moment. And we're going to go over it. That's probably good enough. Okay. E. Should be it. Jacob. Emily. Daisy. Ella. Oh, there you are. Did you used to sit over here? No. Ian, put away your phone before I have to take it. And put it in your bag far away. So, hey, there he is. And Ona. Sophie H. Samantha, I think this should be right there. Yager. Oh, there you are. Hazel. Where'd more? Oh, there's Morgan. Jensa. Liv. Go. Max. Where's Max? There's Max. And Sam. No, and Riley. Anybody who did not get one? That's the other class. That's the other class. That's yours. You got bumped in with a different block. Okay. For the this particular one, a lot of you will have. Ooh, do I have an older one? I'm going to copy it from up here. Oops. probably lock that one as well. Emiliano? We'll be going over it. And then you can ask questions. Okay. I think most of you have this written on there. If I forgot to write it down, this was the my little marking grid. Number 1, the axes. So the axes were that you had picked some sort of proper X and Y axes. The instructions were that they needed to be labeled. And you didn't need a numerical scale for the time axis. You also know that it has to do with temperature. So the graph would be time on the bottom. You have to label time, temperature. Exactly. So if you could wait, because I am going to go through it. If you don't include the units, you don't have a graph. You have a random selection of points, and we don't know what they are. So if you included the unit in all of the measurements, so you went like 0 degrees Celsius, 20 degrees Celsius, 40 degrees Celsius, that was fine. You can label it every single time if you want. But if you're not going to label it every single time, which would probably take you way too long, you can put it right in the axes. Well, that was under scale. So this was axis, time, temperature. So that was 1. And then you needed a reasonable scale. So a reasonable scale is one that takes up more than half the page but doesn't extend beyond the page. And this one goes from 17 to 139. So you need something that goes through all these points. So probably a reasonable one would be one like 0, 20, 40, 60, 80, and so on. Now, a couple would have, you should also indicate where the actual axis is. I didn't worry about this too much because it was reasonably obvious, but you should always indicate where your axis actually is and where the graph actually starts and where your numbers are just poking out. If you did it like this, that's a reasonable scale, but a few people in all the classes would do something like, oh, I need 17 and 139, so, this is 17, and then that's 139. That's not a scale, that's just 2 random points, and I'm looking for the scale. You didn't need one for time, but you needed one for temperature. And in a couple of cases, they also did something like 20, 40, and then they go here and go 139. So it started off with a scale and then just skipped a bunch of things. So the scale was that you had a reasonably working scale. A couple of other things that some people did is that they ran out of room, so they just drew more. Can't do that. You have to actually go through and make the scale fit the graph. That would be under communications in an experimental setting. We need to actually see the graph and not cover up other work. Ian, question? Hand? Yes? Sorry, I couldn't quite. You didn't. This is grade 9. This is actually grade 9 graphing. I'm going over one question, so the first one, And graphing skills, like how to graph, is grade 9. Actually, grade 8. I know they actually teach it here in grade 8 because I've checked. And so normal graphing, when I ask for a graph, I ask for a graph. And these are axes and scales. If you didn't get this knowledge up until this point, then you've got this test to figure it out. Because then you won't have to worry, or this quiz, because it is formative. But in a senior lab course, I expect a regular graph. I don't expect you not to know how to do a graph. That's the difference in a formative and non-formative, is that this one you can do better on. But if you don't have a unit, then you didn't do a graph. You gave me some random numbers. So that was a mark for scale. Now the next one, oops, and that one should be 17/139. Line pure and line mix. So we know it melts at 17 and it boils at 139. So we need something that shows that. Here's my 20, so I'll put, that should be about 17. And 139 will be right. Let's put it right there. And here, this is for your line for the pure. I'm looking that you have a plateau in both cases. And then so straight, plateau, straight, plateau, straight. So here we have the melting point, and here we have the boiling point, and the temperature does not rise at those points. So this is identical to the water graph that we drew in class when we went over pure substances. They do not change in temperature when they are when you're increasing the temperature until all of the phase is gone. So this is solid, solid plus liquid, liquid, liquid plus gas, and gas. And so until all the liquid's gone, the temperature will not rise. So labeling those phases properly is a mark, and then having that with a plateau is a mark. The mixture, once we've added, what did we add to this one? We contaminated it with water. Now for this one, contamination, I don't care what temperatures there are. You can shift this graph in any way you like, but what I'm looking for is that in both of these cases, and let me do that, and I'll pick something like blue to mix that. Let's do that one. Is that we no longer have a plateau, but where a plateau would be, the slope is just slightly less. So mixtures don't have melting points, they have melting ranges. Yes? Did you have solid plus liquid and liquid plus gas? It's only one mark. You forgot two things. It's not worth a mark. I'm expecting that students know what solid, liquid, and gas are. But the fact that the plateaus are both of the phases together is the key chemistry 11 part. Oh, it will show me afterwards. If you wrote it in there and I didn't see it, I'll want to see it. So solid, solid plus liquid, liquid, liquid plus gas, gas. And then this spot, there are no plateaus. Mixtures, because they have two substances in them, don't have melting points, so they'll melt over a range. So the example is like salt water. Well, instead of melting at 0, will start melting at -5, which is why people throw salt down when it's cold. And it doesn't finish melting until it's like +3. So it has a melting range. Yeah, so it's just, instead of having a plateau, it has a slope. And that is the chief difference between pure things and mixtures. And then the 17 and 39 is, we told you what it was, and you graphed it. Did you make it at 17 and 139? That was the last point. So was your graph consistent with the temperatures that I gave you? Sure. You've been in a place where they put down salt to melt the water in the wintertime? Yeah. I mean, they do it here. They don't do it where it gets really cold, though. A lot of places in the interior, they don't throw down salt because it's too cold. But if you're in a place where it gets down like -3, -4, -5, they throw down salt because that lowers the melting point below 0. Now, it's still water, but now it's water plus salt. Instead of melting at exactly 0, it will melt in a range. So in this case, I wanted to see the range. So if this melts at 17, the mixture should melt below 17 and above 17 and have a phase where you have the solid and the liquid. So when you throw salt down, you will have a phase in which some of the water will melt, some of it remains as ice, and you get both of them over a larger range. Oops, erase that time. Any questions on that one? This is being recorded, so you'll be able to go back and review it. So it is being uploaded. Next one, atomic number of cobalt. Atomic number of cobalt is given right here, 27. And given on the top is the mass number. So the number of protons, same as the number of, same as the atomic number. Number of neutron is those two minus each other. This should be 33. And it was a +2 ion. So the number of electrons should be 2 less at 25. Half a mark each. Oh, sorry, I thought it was a hand. For isotopes from last year. Questions on that one? Always. The atomic number is just a fancy word for number of protons. Yep. The following mixture of isotopes are found in nature. Calculate the expected atomic mass, molar mass of the sample or mixture. So we have 20 neon, 21 neon, and 22 neon. I should probably fix this down. So you have 90.5% over 100% times 20. Do that all 3 times. And I don't know if I have those. I probably don't have those written down. So what was the first one? 18.1. Second one? And the third one? 2 point. Excellent. Units are AMU. If you get tired of writing AMU when you're doing this, you can just use U. That's an acceptable unit as well. And then you have atomic mass equals 18.1 U plus 0.0567 U plus 2.046 U, which is then equal to the total, which comes out to 20.2026 U. If you rounded the last answer, you can, although we haven't done the rules of rounding. We're going to be doing that in the future. That's called significant figures. Do not round in between. You'll get the incorrect answer. When you round in between, you're taking away some of your accuracy. Well, technically, you're taking away some of your precision. So you can't round here. You can round there. As well, if you have a habit of doing something like this, don't do that, because these things don't equal that added up to those things. You've created an equation that isn't true, on just sort of on a technicality. And I see a lot of times when students are working on physics or chemistry problem, they'll get an answer they have to use for another step, and they start using it right here and start like multiplying or dividing exactly what they need to do for the next step. But that equal sign means that these things on both sides have to equal each other. You're not laying out your work in a way that is actually true, and that makes a mistake in your work. Use the extra paper and show a next step if you need to show a next step. Rewrite it out so it's very clear. This is not only practicing to show the answer, but also practicing to show the communication of the answer, whether you're writing a lab report or a scientific journal or writing an essay. Questions on that one? Okay, last one. Explain the trend as you move across a period. Across a period, now this should be in full sentences. As you go through, but here's the main 3 points I'm looking for. State the unit, explain the trend. You have to stay what the trend is. So ionization energy increases from left to right. It's the energy required to pull off an electron. If it increases from left to right, and it's the energy to pull off an electron, what is the reason for the trend? Well, from left to right, the number of protons increases from left to right. Am I in the way? Sorry. Oh, and we're doing way down there. And then the last one, you have to link those two things together. An increase of protons is an increase of attraction to the electrons, making them more difficult to remove. So these are the two things that are involved, and that's how those things interact. Now, a part to be careful here is not to say too much. So a number of students, for example, would start off saying, as you move from left to right across the periodic table, the ionization energy, increases. You've said it correctly. But then you tell me that the atomic size increases as well. You've given me a trend I haven't asked for, and your statement about it is incorrect. Or you start talking about, as I move down a family, there's more shells, and so you start talking about the shielding effect. Now, all of that is irrelevant. I didn't ask for it. And if any of it's wrong, I can't ignore it. Because if you said something that's incorrect, then you actually don't understand trends on the periodic table in this answer. Remove. This one. Remove. So be careful about adding things that aren't required. Just purely on a practical thing, if I have asked you for a trend on ionization energy and it's across the periodic table, you don't need to talk about down on the periodic table. Now, on an overall basis, it'd be great to mention it, because then I know whether or not you really understand it. But from a practical student writing a quiz perspective, you probably don't want to start explaining paragraphs of things, and then I find something that actually is incorrect within there. As I saw there's transcripts of lawyers online talking to the judge who is deciding in their favor, and instead of shutting up, they keep talking, and then the judge decides against them because they managed to say something that destroyed their own case. You want to talk about what I've asked, and not really a lot extra, because unless the extra really helps you. If for some reason you needed to explain the shielding effect in order to explain the other effect, then great. Or if it added something to it. But if it doesn't add something to it, you don't really need it. If you wanted to use atomic size to talk about the concentration of charge, you didn't really need to, but if you use that, then that would have been fine too. In fact, that could have replaced one of those points in some cases, so it might have been okay. So this one was out of 3. If I didn't put it on yours, this one was out of 5, so you got a mark there. Oh, this is an important point. 1 for each calculation. 1 for the adding up. Half a mark for the units. And half a mark for the actual answer. So the numerical answer is only worth half a mark out of 5. Because at this point, grade 11 chemistry, I don't really care if you get the right answer or not. What I care is that you have the right method. Because if you have the right method, then in the future, when it matters, you're going to get the right answer. But right now, do you know how to calculate all the different steps? Do you know how to add them all up together? And then do you know the importance of their units? The European Space Agency and NASA crashed $18 million on Mars because one part of the team was using imperial units. The rest of the team, and indeed the rest of the world, uses metric units, and they forgot to communicate their units back and forth. So instead of landing the lander gently on the surface of Mars, it accelerated and actually smashed itself to smithereens, and they lost. They got it all the way there, and they didn't manage to land it. Units tell us what we're dealing with and the quantities involved. There are other units that you could use here. Technically, grams can be correct for reasons that will become apparent later. So I accepted it if you used that. And I think in terms of this one was out of 3, even though it said it here, that was supposed to be on this line. And then this one out of total was out of 6. Questions on the whole thing? Okay, you get to keep that. Put it away in your book. My voice cracked there for a moment. It must be my second puberty. Yes. Do I have a... You can just rewrite out the questions if you need to. Oh, I can get you that. Yeah. Sure. If you email me, I'll post one to the classroom. And then everybody who would like to redo that can do that. Pull out your notes. There it is. Oh, yeah. Today we are getting into the nitty and gritty with sublevels. and it's going to be so much fun. Quantum theory E. What's that one? Sir. Yes. What is it? Oh, yeah. Go ahead. That is why they're there. That should go in there. Oh, Yager, I haven't taken it out yet, but don't let me forget. I have your Hebden. Come on. Come on. There we go. Okay. We did this last day? And we did that? Excellent. And did I show you this? It goes up and down? Nice. And you got a copy of that? Not a copy? Oh, okay. So that's where we are. So now... And so if we did that, did I make you draw this? Excellent. Draw this. Just that. 1s, and then 2s, 2p, then 3s, 3p, 3d, then 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. If you're wondering why there isn't a 6f, it's because we haven't discovered enough elements to go up that high. Those are all the suborbitals. So here's the first energy level, the second energy level. So this is n is equal to 1, n is equal to 2, n is equal to... So these are all the energy levels of the atom. No, this is going to allow you to figure out that. There's a couple of ways that you can use it, and I'm just going to show you how. First, draw it out because it's easier to show you once you have it. What? Come on. There we go. It's not wrong, you just won't need it. If you ever manage to need 6F, it won't be wrong. You'll have won a Nobel Prize. So if you'd like to include it, you can. But this lets you know all the ones that exist. It's kind of symmetrical. We're just missing the 8s on top. And the reason we're missing the 8s on top and why it ends, first energy level, second, 1, 2, 3, 4, 5, 6, 7 elements that don't exist. The 8s is not there. And I'll show that with the periodic table in a moment, but it's not there because we don't need it. Yes, yes. If you, in fact, if you discover a new element or some other crazy, really Nobel Prize winning thing, you do need to be really careful because there's people out there that will take advantage of you. So bring it to me and I'll take care of you and your mark. No worries. Yeah. You'll never have to worry about anything ever again. And that didn't sound creepy at all. Okay. Now hold it. Why is this? Oh, somebody didn't erase it. Let's go open that one. But while we're waiting for it to open. So, now that you have it, this has some peculiarities in that Whoa, stop that. Done. There we go. 1, and then 2, and then 3, but 4 comes before 3, and they go in between. This is a trick that I learned in university, especially when I never got, when there were some tests where I never got my periodic table, and I'd have to figure things out from what they left, is that you start at the bottom, just like you start at the bottom here, and it fills up in the order of the arrows if you point them up. So this is the first, second, third, fourth, fifth, sixth, yeah, seventh, eighth. And what you're doing is, if I was to follow this along, I would have, okay, this one fills first, 1s2. And then when you're done, you go to the next energy level, and it goes 2s2. And then that goes to the next energy level, which is then 2p6, 3s2. And then when we go 3s2, and then here, 3p6, 4s2, and then it comes here at 3d. So it's correctly put in the d, and it would be 3d10, 4p6, 5s2, and you can keep going. And so it fills up in this direction. The 4d fills up before the 5p, which fills up before the 6s. And so you can keep working through this. So it's a quick little way. You make a little triangle like this, start at the bottom, work your way up. Some of you may, now I didn't show you this last day. So if you, some of you, I know, because I know some chemistry teachers flip it. So they'll go 1s2, sorry, 1s, and then 2s, 2p, and then 3s, 3p, 3d. And it's the same thing, except instead of doing it down, you just have to do it like that. You have to point them down. So if you did see it in a different class and you did it that way, don't rearrange your brain, just keep using that. It's exactly the same diagram. Just depends which teacher you had and how they learned it. For me, this fills from the bottom up, and so I fill this one, the other one, from the bottom up. So this is a useful way to generate it. What order do these go in? And you can use this to generate the order. It's 1s, 2s, 2p, and you can see which one's next and which one's next all the way along. Now the other thing, especially for you, because you always have your periodic table, is that you can pretend your periodic table corresponds to the subatomic structures, to these energy levels. We did this when we did Bohr. I showed you that the first energy level has 2, the second energy level has 8, the third energy level has 8, this one here has 18. But now we can see it corresponds even more closely than that. If you pretend this block is the p orbitals, this block, and you have to shove this one all the way over here, are the s orbitals, and these are the d, and you can count to 3, because I don't think we're ever going to use f, so technically that'd be 4, but 1, 2, 3, and this is S, P, and D. And then it just continues down from there. 2S, 3S, 4S, 5S, 6S, 3D, 4D, 5D, 6D, 2P, 3P, 4P. What that's so those so these are all like 3P is there. So if I ask you, for example, let's say we're going to do nitrogen. Nitrogen is right here. So all the elements counting across for nitrogen, I'm like, okay, I'm starting at the 1s. So I'm 1s. This is for nitrogen. And I just start counting my way along. So 1s, 2s. I've got 1s2. Then the next one, I go to the next row, 2s2, because both of these are counted. And then I'm starting the next row, so it's 2p, 1, 2, 3, 2p3. So the work we were doing last day, you can count right off the periodic table. You don't actually need this particular diagram, because you can also generate it this way. So if I was to ask for something complicated, like gallium. Sure, gallium is over to the right after zinc, so let's do gallium. So gallium. Again, starting at the beginning. I take out both of those, which is actually that one, so I've got 1s2, 1, 2. Going across, this is now the 2s, and I fill it up, 2s, and there's 2 of them, 1, 2. Then I go over, here's the 2p, 1, 2, 3, 4, 5, 6, 2p6. End of the row, come down, I'm at the 3s, 1, 2, 3p, 1, 2, 3, 4, 5, 6, 3p6, counting to 4s2. And then I have to remember that the number now decreases. So it's 1, 2, 3 here. 3d, counting all the way to the end, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the last one with gallium, that would be 2p, 3p, 4p, 1. No, you have to put in the number. You have to put in the number. Yes? Yeah, so if you, I mean, it's just way over here. So you go helium, if you were doing it, would just be 1s2. Yeah, yeah. I mean, mentally, as long as you just remember that the first one's the S, whatever works for you. So to do a couple of examples of that one, let's do, using this method. Now, take this, put it on your periodic table in some way, and because I'm so nice, I've photocopied a version of the one you've been drawing, the triangle I've just given you, and a copy of the color-coded periodic table. Pardon? Yeah. Oh, it's terrible, black and white. I'm going to give you this, and let's do a practice. Oops, go away. I want you to use this table method, and I want you to try potassium, oxygen, and let's do lithium. And I'll call 3 people up to actually do it on the board. We'll call this row salmon. Hummingbird. Pardon? Sure, I'll pull them out in just a second. Let's say deer. The Vancouver Island marmot. The marmot. This row. Trout. Where? Where did I not? Oh, right. Yeah, we do. There we go. Trout. Trout. And then, hello. Oh, upstairs to the office where Mrs. Mertland is. Ask there. You hand in textbooks there. They'll take off your number eventually. Yeah. You're welcome. And then honeybee. Honeybee. That is, your rose is the name of the small forest or fish or insect creature native to Vancouver Island that you just killed in order to use all the paper I hand out so that you can think about that. So if you never use this, they died in vain. When you log, you destroy riverbeds. Salmon are at most at risk of all, actually. Yeah. And the Vancouver Island marmot is in near extinction. There and then there, or there. Oh. The one I was drawing on before. This one. Yes. Yes. And you want the pencil crayons. Now there are some pencil crayons if you would like them. What is it that you need on the notes? But I just gave you a photocopy that has all those on. Okay. It is recorded. Okay. No, that's fair. And then the actual, are you good with that one? Okay. Then the ones you're actually doing is potassium, oxygen, and lithium. And I will ask, pardon? No, you're not even supposed to mention that yet. They don't know about it. Nothing? No, younger.
You talked about it last time.
Did I?
Yeah, you definitely said that there is that, and that we're gonna be
I don't think I said that. How you doing? Oh, so you're well on your way. Yeah. I find the periodic, because you will always have your periodic table, it's probably the most useful method for you to learn. Yep. That's sulfur. So I just picked this off the internet, and they randomly put some elements in there. How are you doing, Hazel? Excellent. Okay. Yep. Yep. For F, 5P would become, and 6S would become before 4S. We haven't put in the other ones in there, and I didn't give you any examples with that. It extends further. Use this method instead. Yeah. For the first one, potassium, you can come up, grab my pen. Oh, I should quickly do attendance. Emily, Daisy, Ella, Emiliano, Hazel, Ian, Jacob, Yager, Jensa, Liv, Lorelai's not in the course, Max, Morgan, Ona, Riley, Samantha. Oh, that's good. Sophie, good. So, for the first one, Yager. Can you do the first one? Yep. Okay. Oh, you can write whatever you want. It's not a touch screen, so your hand can go on it. It's pen. If you press the button, it will write E. So don't press the button. I don't know why it does that. It just does. Good. Well, do the next ones. Oxygen and the one after that. There. This is all good. Oh, it's lithium, right? That is short. Excellent. Excellent. Yeah. Yep. How are you doing? Oh, where's the K, O, and L, I? Where are you writing down the answers? Oh, well, you need to look at this at the same time. Use your notes. Yeah. And while we're waiting, next up, Ian. Oh. It looks good, yeah. Flip over your map. Let's follow along on yours. And put it beside it. Let's do potassium. So circle or put a K where potassium is supposed to be on there. Oh no, where's your periodic table? Oh, okay. Okay, so you have K there. So what's, just reading from the top from left to right like you'd read a book. What's the first energy level? 1s. So write 1s. How many are in that row, in the 1s row? 2. So put a little 2 up there. That's 2 electrons. Don't need to do a comma. And then start the next row. What's the next suborbital? Write that down. And how many there are? Yeah. But you keep going across. What's over from it? Nope, over from 2s. Follow it straight line. Yeah. Yep. Yep. And now when you reach the end of the row, then you start over. Yep. Yep. It's just sulfur. Like if you look at it, it's just, yeah, they just put some elements in there to help orient you. Okay. Yes, you want to do the last one? Perfect. Yeah, 4s1 because there's only one in it. Yeah. Excellent. This is one of those areas that looks really arcane, but actually doing it is really easy. Yeah. Because we don't have to do any of the math. Excellent. Oh. If you're ever worried. Sorry, what? Oh, I see, yeah. No one will ever know. For these all look, oxygen, these all look good. As you're doing these, or not as you're doing these, when I call you up to the board, as you may have noticed if you came up, I try to always have the answers on this screen. So if you're ever like totally panicked, I need to check it first. It should be right here. And if it's not, you're allowed to ask me, because this shouldn't be a hugely stressful part of your day. And if it is, then you need help. That's part of what I'm checking. I'm calling you up so like if you don't know how to do it, you can look and ask and get that part of it. Okay. Another page. Turn over. I would like you as an example, to give me the electronic structure of oxygen -2, neon, and fluorine -1. So we're going to add some negative ions in here. Say that really loud. Oh, I'm not going to confirm. I just asked you to say it really loud for completely random reasons. Oh, say that really loud. Mm. Mm. I want what we just did. Do it for those. What we just did. No, 1s2 and onwards. Oh, yes, it might. I mean, I don't know. Ah. Say that again, but without the weight in front. 3 elements. Oh, and what? It does, because everybody has done just enough information and finished their units by just before midterm. Yeah, that's always the way. And then everybody's like, did the teachers plan it that way? No, it's just how you give out information. You don't give it out when you've only done like a couple of weeks. Pardon? We're not quite done quantum. So probably not the end of this week, but definitely at the end of next week. But I have to consult with Mr. Snow, because we're going to do our test, and the Chemistry 11 APs are hopefully going to do their test at the same time. So he might push it farther ahead, because apparently they're not as far ahead as we are. Well, they actually did different things. Yeah, they're adding a ton of like we do this, and I've told you about the Pauli exclusion principle, but they've done the de Broglie equation, and they equate it to a lot of other things while they're doing it. So they do more in it. And so it's not, AP isn't cognitively more difficult. Some students drop down and they find their mark doesn't go up, and that's because it's equal in difficulty. We just cover a little less material and go a little slower. Yeah. Well, they cover more. The de Broglie equation. No, we're not. You may have done it in physics. Yeah. They do it, and they relate it to this in chemistry. Yeah. Okay. What is this one? Please. Oh, I should just go for who needs more points. Ella. You only have 1 point. That's terrible. Okay. What would this one be, Ella? 2s2, 2p6. And weirdly, what would neon be? And fluorine? Exactly. So if you have a negative charge, you just add those particular electrons, and everything wants to become like the nearest noble gas, And so it's hardly surprising that they end up like the nearest noble gas. This is something. So definition to write down. And I'm going to grab it from here so I was going to write it. Yeah, yes it is, but also no. There's a very deliberate reason that I haven't put any positive ones in there, because when you take off electrons, there's slightly different rules. Remember when I showed you that some of the orbitals when full go down? Well, that changes which electrons you take off first. Yeah. So I do that as a whole section after this. It's like the last thing we have to do. Isoelectronic is two or more elements that have the same electronic structure. So all of these are isoelectronic. I'll give you some positive ions next to do, but I very carefully give you ones that aren't going to do that, yeah. As well, I'm going to rewrite these. And what I'm going to rewrite them as, actually I'm going to give myself a little room here, but you can put this underneath, is that the electronic structure for helium is equal to 1s2. Does anybody not know where I got that? So I'm going to rewrite these as structure of helium 2s2 2p6. Structure of helium, so I take that out. So all of the inner shells that aren't valence electrons that you then just get rid of. Now for this one, that doesn't save you a lot of room because it's helium and helium's only 1s2. But if you can imagine if you're doing something like strontium, you could just do square brackets krypton and then just do 1s2. And then you'd be done. Emiliano's very happy because this is known as core notation. Nope, you can just write it. If I say I want the full electronic structure, that means no core notation. Can you also what? Do beryllium? You may write down any examples you like. Oh, if you would like to, sure. It is for this example. But if I did, for example, the one that I just said, let's do strontium. Oh, there's the actual thing I just said. Go away. So for example, strontium. SR. Yes? Right. What is this? What is the electronic structure of helium? So I just take that out and write helium instead. Take 1s2 out and then write helium in square brackets. Yeah. Oh, because strontium, which is right here, I could write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. No. Now I can do this. I can go krypton, and I skip all of that. And I go 1, 2, 3, 4. It's 5s2. Yes. So what you can't do is, let's say I have oxygen -2 like we just did. I can't go up here and then say, oh, square bracket neon. You only do it for non-valence electrons, so it always has to be the previous noble gas. So when we're working with strontium, it has to be the previous noble gas. If it's chlorine -1, I have to use neon, not argon. The last noble gas it passed, yeah. Yeah. Because those are non-valence electrons, and so we can ignore them. Yeah, you don't make a mistake halfway in between. So let's do in that chlorine -1 and yttrium. You can't use the noble gas in the same shell as its valence electrons. So you wouldn't use AR, but you could use. Oh, that's the next one up. It's it doesn't even have those electrons. Neon. Is isoelectronic with AR, but those are the electrons we're also working with. So we still want to write them down, because if that chlorine does something else, we've locked them in terms of symbology, we can't use them anymore. Yeah. You'd use. So for Yager, you include the last row it's in. Does that answer your question? Okay. Yeah. If you want to, you will get questions where I give it to you in core notation, and there may be a question where I want to check if you can do it in core notation. I say, please do it in core notation. But if it doesn't say either way, you get to choose. Yep. Who else needs more points? Why? Yeah. Why you wouldn't use magnesium? Oh, I see what you're doing. You want to do you want to go like, right? Is that what you want to do? Yeah. No. Oh no. A little brilliant. But the reason we don't do that is the 3s2. Those are still valence electrons. They'll still do stuff. And so we only do noble gases, because once they've reached the previous noble gas, those are locked away, and they're not going to do anything anymore. You can't take them out. They're not going to become part of an ion. You're not going to add to them. You're not going to take away from them. And so they're totally locked down. These can still participate in bonding. So when chlorine is sharing electrons, those can still be used, and so we want to see those at all times. So we only noble gases. Yeah, the previous one, the one previous. So Daisy, what would yttrium be? Oh, have you found yttrium yet? Pardon? Krypton, yeah. Yep. 5s2. Somebody said incredulously, so I will look. 1, 2, 3, 4, 5. Yeah, it's definitely 5. And then 4d1. So a couple of things. Good. You recognize that that number wasn't 5 because the d orbitals start at 1 less. So the d orbitals start at 3, so the next row down would be 4d. Perfect. Hmm. 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 So it is, yeah, it's 4d1. Yeah. We're going to skip that. And I'm going to hide that. Does it matter if you use square brackets versus rounded brackets? Yes. It's just because that's the criteria that they've used. It's square brackets to distinguish it from other things that we put into rounded brackets. So it's a bit like, do you always have to capitalize the beginning of a sentence? And the answer is yes, just because that's what we've said everybody has to do. No, now we're doing valence electrons. So, using core notation, let's use vanadium and gallium. But you have to use core notation. We've already done gallium once. I think that was the example that you wanted. So use core notation. Give me vanadium and gallium. Yep, core notation is the square brackets. And who do I need to give more points to? Oh, Ona. Ona? The one for vanadium, whenever you're ready. Nice. Excellent. And then, who needs more points? Sam. For gallium. And beside all of them, number of valence electrons. And I'll ask you to guess for the first one. And I'll say the first one is very straightforward. And I will ask, Liv, how many electrons are in here? How many valence electrons do we have? First one. 5. And the next one, I will start off by saying it's a trick question. But if you remember how we counted valence last year, then this should give you a bit of a help. Samantha, how many valence electrons would you predict? It's not, so you assumed correctly. So last year, what did we do when we were counting across the transition metals? The rhyme was 1, 2, skip a few. So it's 3. Excellent. And that was a trick question. Because once this is locked away, this goes all the way back to what I mentioned here. Once that d orbital is full, it goes down so that it's underneath, and now it doesn't count. It's not in the 4th energy level. It's not a valence electron anymore. Oh, then it counts. Just when it's full, it doesn't count. Yeah. So this has 3 electrons, valence electrons. And this is why the transition metals can have such pretty colors. They engage with bonding because they have access to those d electrons that other elements don't. But once they're locked up and put away, we don't consider them part of the valence electrons. Yeah. Oh, they would have their full amount. So copper would have its 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. But this explains why zinc technically has those 10 and never uses it. The most common charge for zinc is +2. It just gets rid of those 2 and it never uses them. Yeah. Yeah. I will put this back up next day. If you didn't write this down, you don't have to worry about it. We will do that. Next day we'll probably finish up. And then the rest of the block will be a catch-up study day in preparation for the test. Yeah? Copper is 9. 9 plus 2, 10, 11. Yeah. Thank you.
Do you know what day the test is going to be?
It depends what day we have class next week. So today is a Monday. So next week it would be on Thursday.
No, but they skip it on Wednesday. It's not like that day.
I will have to double check.
Okay.
Because we have Wednesday, we have like what? Wellness.
Like you're just missing that day.
They move it. I will have to double check then to see how they.
Wednesday, Thursday, or Friday.
No, it'll be Thursday or Friday. Thursday or Friday. Unless I like putting it before a lunch or a break, so yeah, I'll have to double check that.
Should we have longer to
Yeah. So if anybody needs it, I don't want to stop anybody who wants extra time. You're welcome. If that's yours, grab it. It's just been sitting there. I do, however, have to consult with Mr. Snow, because if he says no, it can't.